Okay, so today we're going to talk more about how to convert a velocity versus time graph to a position versus time graph. So just as a reminder, we know that the area under a velocity versus time graph is displacement, which again, displacement is our net change in position. And I always think of it as like the units canceling out, which I love. So let's say I'm going 3 meters per second, and this is my velocity versus time graph for, let's say, 2 seconds. So if I think about it, I go 3 meters per every 1 second. So that means after 1 second, I go 3 meters. After another second, I'm going to go 3 more meters. So that's going to be 6 meters total. And if I look at this beautiful little graph right here, cool. The area under this, so this rectangle formed with the x-axis, is 3 meters per second times 2 seconds. The seconds cancel off, and we're left with 6 meters. So always think about it as the units kind of canceling out to get what you need. Units give us a ton of clues about what we can find. Cool. And one thing that I'll add is the area under a curve is called the integral in calculus. So we'll use both terms, the area under the curve or the integral of the graph. Perfect. So now we're going to go through an example. Okay, so we're going to convert this velocity versus time graph to a position versus time graph. So I'm going to go ahead and label my axes. So I'm going to measure this position. Time is in seconds. Perfect. So next thing that I do is I go ahead and split my velocity graph into sections of the object doing different things. So I'll go ahead and we have one section right here. Right here, that's supposed to be at 5 seconds. Sorry, my thing isn't perfect. One section right here. Looks like we have one section. I'm going to say, just for my math purposes, that's at about 7 seconds. And then I'm going to say this is at 11 seconds. And then we have this section right here. Cool. So I'm going to say first step is split into sections of like the object doing different things like velocity-wise, like whether it's speeding up or slowing down or constant speed or rest. Now what I'm going to do is I'm going to label each section. And I think this is really important to do before you do any math. And with that labeling each section, I'm going to add two things. Both like sorry about that move, is A, what direction is it moving? So is the object moving in a positive or a negative direction? And again, if the object is moving in a positive direction, the velocity is positive. If it's moving in a negative direction, the velocity is negative. And then I'm going to add in how it's moving, whether it is a constant speed, speeding up, slowing down, or at rest. Perfect. So I'll go ahead and label that for each section. So this first section, it looks like you're going 2 meters per second. So that's a positive direction. You're always going to, so that's constant speed. This next section right here, so you're going from 2 meters per second to 0 meters per second. So it looks like you're still moving in a positive direction because your velocity is positive, but you are slowing down. Cool. So then this next section right here, so you're going from 0 meters per second to -4 meters per second. So you're speeding up, but in a negative direction. Your velocity is negative, so you're moving in a negative direction, and you're getting faster. Now this part right here, I'm going from, this is 7 seconds, this is 11. Okay, so I'm going -4 meters per second the entire time. So I'm moving in a negative direction, and then I'm going at a constant speed. Now the next part, look, my velocity is 0, so I'm just at rest. And one thing I should have labeled earlier, when you switch from moving in a positive direction to a negative direction, you're going to turn around. And at that instant you turn around, it's impossible for your velocity not to be 0 meters per second when you turn around. So that's going to be your velocity right there. Perfect. So now we know our next thing is going to be to go ahead and find the area of each section. So find the integral, so the area of each section. Cool. So so I'm going to look at this first section right here. So the area of just this portion right here. So that has 2 meters per second by what, 3 seconds? Oh, that's like the example we just did. Or not exactly, but close. 3 seconds. So the units cancel out, and we're left with 6 meters. So fun. Okay? And again, it's the area it forms with the x-axis. So it's this little one right here, and I love just like practicing my areas right there. So this right here, so we have a beautiful, oh gosh, I can't outline a triangle. We have a beautiful little triangle. So the height of the triangle is 2, and then the base of the triangle, we go about from 3 to 5. So the base is 2. So the area is going to be triangle, so what, 1/2 base times height? So 1/2, 2 seconds is the base, and the height is 2 meters per second. So seconds cancel, and then we're just going to be left with 2 meters. So this right here is just 2 meters. Perfect. Sorry, a little sloppy. So now let's look at our next section. So we have this one right here. So good old triangle right here. I'm going to do it down here where, but then I'm intruding on my other space. I'm just going to erase this, turns around at 0 meters per second. We know that. We'll come back to that. So the area is 1/2. The base is from 5 to 7, so that's going to be 2 seconds. Times the height is from 0 to -4, so the height is -4. So that's going to leave us with -4 meters. And if you say something slightly different with me, that's totally fine. Cool. And so then let's look at our next section. So I'll do this one in yellow. Cool. So we have a good old rectangle. It almost looks like a square. So the area is the base. So 1, 2, 3, 4. 4 by -4 is the height. Cool. So -16 meters. And then this last part, we're just at rest right here. We're on, like the line is literally on the velocity versus time, like x-axis. There's no area there. So that's 0 meters. And that makes sense because we're at rest. That's so cool how physics makes sense. Cool. So now what I'm going to do, so step number 3, after I find the integral, I'm going to go ahead and graph. One thing, make sure when you start graphing, check the starting position. In this case, it looks like we start at the origin. But some cases, we might start at like, I don't know, different thing, like x equals 2 or x equals -2, whatever. So I'll start right here. So now, we're going from where we start, we're going 6 meters up. So it's going to be 1, 2, 3, 4, 5, 6. So I always draw my starting and ending point, and then I think about how to connect the lines. So this is a constant speed. We know on a position versus time graph, a constant speed looks like this. Perfect. So now, from 1, 2, 3, 3 to 5 seconds, we go up 2 meters. So our displacement is +2. So 7, 8. And so now we think about how to connect these. So we are slowing down. So that means that my line is going to get like less steep. It's going to get kind of concave down like that. Cool. So now let's look at the next portion. We are going in a negative direction. Interesting. So that means I'm going to have to go backwards from where I was. And it looks like we're speeding up. So we're at 8. We go backwards 4. So we're going to end up at 4. So I'll be like right about here. And we're speeding up. So that means the slope of the position versus time graph has to get faster and faster. So it's kind of like that. And again, this point right here is where you turn around. And at that point, your velocity has to be 0. And if I look at the slope of a line right there, the slope of that line is going to be 0 right there. Cool. Now this next portion, we're going to go backwards 16 from where we are. So we're at 4. We're going to go backwards 16. So we're going to end up at what? -12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. -12. Bingo. Cool. And then it's a constant speed. So a constant speed I have to show by a flat straight line. No, sorry, not flat. I should say a straight line. Excuse me. Cool. And then we are at rest. And again, we're at rest of where we are. We're at -12 meters. So it's just at rest there. Cool. So the last little thing is the problem asks us to find the total distance and displacement. We could do it both using the position versus time and the velocity versus time. I just look at the position versus time one real quick. So my displacement is going to be my final position minus my initial. My final position is negative 12. My initial is 0. And so I'm left with negative 12 meters. Perfect. My distance, I just have to do some good old counting. So I go up to 8, and then I go backwards 8, and then I go what? All the way down to 12? Cool. So I'll just add up how far I go. So that's what? 12, 8 plus 8 plus 12. And so that's going to be what? 28? Cool. Great. And so now let's go ahead and do it using the velocity versus time graph. So we know for a velocity versus time graph, the area under the curve represents the displacement. And we need to keep in those negative signs because direction matters with displacement. So that's going to be 6 for the first one, plus what? 2 meters, plus negative 4 in that, plus negative 16, plus last one is 0. And then that is going to leave us with negative 12 meters. Cool. That's so fun. And it matches up, negative 12 and negative 12, just as it should. So it's a good way to check your work. The distance now, so again with distance, the direction doesn't matter. It's just how far you go. So it's like the total area, the absolute value of it. So I'm just going to add up all these numbers that we found for displacement, but ignore the negative sign. So we have what? 6 plus 2 plus 4 plus 16, and bingo bango, that gives us 28 meters. Perfect. And that checks out. Awesome. Thank you for watching.